So as we look at 3.4 today, we're going to have several things here for us to look at and think about, and you should be taking notes here as we go. But you should definitely be able to fill in these blanks. The instantaneous rate of change is the blank or the blank. This will be the blank if the function is the position function. So take 10 seconds, tell somebody next to you what you think this is. The instantaneous rate of change is the slope of the tangent line. If you said tangent line there, that is incorrect. It is not the tangent line itself, but it is the slope. Or it could be the slope of the function. And this will be the velocity if the function is the position function. So as we review here, just a few things that we should know here as we go. Okay. You definitely could have also said here, just the idea, the instantaneous rate of change is the derivative. That would have been another fine answer to put there. And so again, we just have this overlapping language that we need to be comfortable with no matter how it is stated. So when we think about some other things that you've seen, one of those is definitely locally linear. You've had this conversation lately about whether a function is differentiable or not. You should know the conditions when it is not differentiable. And just to be sure that we don't mix some thoughts here together, when we think about the absolute value function, if I would ask you, does the limit exist for this function as x approaches, let's say that value is -3? Does the limit exist as x approaches -3 for this function? And you should say absolutely yes. And that answer, in fact, is 0. So be sure that you don't lose track of that the answer to a limit is a y value. So we're really looking for the y value of this function. Now, that might sound confusing because we've also now spent a lot of time talking about difference quotients. So here's a difference quotient. This is of the alternate forms, the one that is most important to know. Notice it's really just slope. That would be the main takeaway here that I would want you to notice, is that this is delta y, this is delta x. Change in y, change in x is a slope. And that's the reason that this calculation is a slope. Because the function here that we're really looking at, which is this difference quotient, altogether that is a slope. So if I'm approaching some y value for this entire thing, then I must be getting a slope. So don't confuse that a limit means slope. It doesn't. It didn't just weeks ago. So don't merge those thoughts together. And so here, we definitely have a corner. We have two different slopes. And so we have a slope on the left and we have a slope on the right. As we are approaching -3, they are not the same. So here, there is no slope at -3. This is where we would say the derivative doesn't exist. Okay, so this doesn't exist. And you should know the other conditions. So we have, and these are going to come up again, so we could have some notion of a cusp. And the key element about a cusp is that as we're approaching this this moment, that we have differing ideas of infinity that's occurring, and so the limit isn't going to exist. The one that kind of trips people up sometimes when we go back to it is thinking about the idea of a vertical tangent. And you'll get this wrong if you missed that first warm-up question that I had there. That if I ask you what is the derivative at that value, sometimes people will, well, I can draw a line, right? So the derivative is the line. Remember though, the derivative is not the line, but the slope. So the fact that I can put a line there is something, but now you have to tell me what the slope is if we're going to say what the derivative is. And so since it's a vertical line, you can't tell me the slope, therefore the derivative is undefined at that vertical tangent. Can I draw a tangent? Yes. Can you tell me the slope? No. So back here, and when we think about these derivative graphs we're looking at, every y value is the slope, right? So when we think about, like, you should be able to look at this and then tell me what the graph of the derivative would look like, okay? So we just argued that there's a corner at -3. So at -3, there shouldn't be an answer. Now, if I'm left of -3, I didn't give the function here, but let's suppose that slope over here is -1. So that means that this graph would come along and just be a horizontal line all the way at -3 at the value of -1. And then if the slope over here is 1, then we come up to 1, it jumps up, and now I have my other horizontal line. So we definitely should be able to take these graphs that we've seen and start, and even when they have issues like this, be able to produce some type of graph of the derivative, or graph of the second derivative, or the nth derivative, whatever I might be looking for. So as we get into this, I want to come back here. So take a second and think about sketching this function down. This is a function that you should kind of recognize because it should look like either the watermelon question or the tennis ball problem from last year. The only difference here is that we're not dropping it. We're actually throwing it or launching it vertically in this scenario. So when we think about that function, that -16 t squared plus v initial times t plus the initial height. Notice here there is no initial height, but it does have a starting velocity. Notice that that is positive, positive 160. So for you physics students, this piece right here, you should actually recognize that because it is half the acceleration due to gravity times time squared. So acceleration due to gravity in feet per second squared is -32. That's where the -16 there is coming from. So when we think about that graph, get rid of that, I can move this along. Think about time increasing. So the rocket would be, when we think about what the rocket is doing as it's reaching its maximum point, I'm just decided it's a rocket, I guess. So we would watch it as it's from its launch. We would watch it slow down. Now, I am not trying to sketch the path of the rocket. So I'm really thinking about a rocket that's going straight up, straight down, comes back to the ground. So time is the x-axis, not horizontal distance. So I'm just thinking about, like, this point right here would tell me after whatever this x value is amount of time, that is how high it should be. So as this continues, there's a horizontal tangent here somewhere, right? There's a moment where the derivative would be 0. Now if we think about what the derivative again is saying, so if I had some horizontal tangent that I actually drew at the max there, so the slope of that is 0. Let's think about units here for just a second. So if the derivative is just the change in y or change in x at a single point, that means that I actually know the unit for the derivative. Whenever I'm thinking about calculating the derivative somewhere, so let's say it's some value c, then the answer here has got to be in feet per second. And that's one of the reasons that we are taking a position graph and we are thinking about the derivative, which is helping us understand the velocity. Now, the reason it's not speed is apparent when we think about the rocket. That the rocket actually does two things, like from time 0 till it hits the ground. It goes up, but it also goes down. Now, when we think about the symmetry of the shape, like there's definitely going to be um, tangents that are equal but opposite. So equal slope, but they're opposite direction. So we really want to retain the thought of going up versus going down. So maybe the first observation here is that if the slope of the position function is velocity, and if the velocity is negative, so a negative velocity is always associated with the idea of left or down. Okay, so negative velocity is left or down. And if you think about the coordinate system, negative number, so moving in that direction should make sense. So it allows us then to separate when the rocket is rising versus when the rocket is falling. Now, you definitely now know the power rule, which means we could easily look at this and know what F prime is. And you should write this down in 5 seconds on your paper, faster than I am writing this on my screen. And so I want to, let me rewind this. And let's think about just showing the graph. And let's think about, again, this tangent line. And so when we think about this derivative here that we've calculated, again, all of this entire piece here, should be going into the calculation of slope. And so if I look at the derivative, there's its graph. Now, sometimes when you first see the derivative here of velocity, your instinct is to say something's wrong about it. Let me hide the tangent line here for just a second. That something's wrong about it. Like there's a sense that we don't like, we have a negative reaction to this thought of this part of the graph over here. But thinking about what I just said, notice that there's an x-intercept that should be matching this horizontal tangent, this maximum occurring right here. And so that actually makes perfect sense. And if we roll this back to this moment, now if this is the velocity function, right, this function is telling me the velocity because it's telling me the derivative, it's telling me the rate of change of position, then that means that this y value, actually, do you notice, because the power rule, it is this number? Which goes back to why I said that this is the initial velocity of the function. So here's what this means. Those of you that were in physics and had to you felt like you needed to memorize a bunch of different formulas for position and velocity, well, most of them are just derivatives or going backwards from the notion of the derivatives of each other. So this portion of the graph down here for the derivative is just really showing us that the rocket is coming back down. So when we think about this y value here, like this y value, which is about minus 100, should be corresponding to the slope of the tangent over here. So if I put the tangent and we look at all of these pieces together, oops, drag this around over here, and we think about these points. And so if we're tracking with this, that means that if I would have Sketchpad tell me what the y coordinate here is, looking at the screen, you should know what it should be. I hope that's what you were thinking. Because this is the derivative, its y value should be the slope of that original function. Okay, so here is then the graph of the derivative. It tells me the rate of change at every single moment. But you notice I have another graph here this dark blue one, which is the derivative of the derivative, the rate of change of the rate of change. Now, that is just the second derivative of this function, which is the first derivative of this one. Again, power rule, super simple. The answer is -32. And that number is not a surprise. Now, first, let's think about units. If this function has a y value of feet per second and an x value of seconds, its slope should be feet per second, which is feet per second squared, which is a unit acceleration. In fact, the only acceleration that this rocket is experiencing is, well, gravity. And that's exactly why this y value here is at -32, because the acceleration is constant. It's just the gravitational force that's acting upon. I'm going to delete that, clean this up. And so just then looking at this like all together, notice that these three functions tell us an awful lot about the rocket. I can figure out which way it's moving. Is it up? Is it down? I can figure out if it's speeding up or slowing down. I can really just describe most of the motion just by looking at these three curves. So I wanna just point a few things here out. Notice at this moment the rocket should be slowing down, right? We're approaching the max. Notice velocity is positive. Why positive? Because it's going up, right? Tangent line tells us it's going up. But if the velocity, this is a good thing to jot down, if the velocity and the acceleration have opposite signs, we should be slowing down. If velocity and acceleration have the same sign, we would see it as speeding up. And notice that that's what happens on the other side. So if I would move this over here, rocket's coming back down, tangent line, negative slope, negative velocity. So that slope is this y value. But if we were watching this, right, we would see it speeding up toward the ground, moving faster and faster. Acceleration and velocity have the same sign. Here they're both negative, thus speeding up. Okay. Always going to be a few questions, even on the AP test, seeing if you will mix up speeding up or slowing down. A lot of times people just say, oh, if they're both positive, and forget that if they're both negative, that would also be the case. So with that, I want to do some other things here, looking at the derivative. As we think about these things in general, so I have a function here, some cubic, doesn't really matter. I have a tangent line on it. I can move this line about. And so when you're thinking about these series of functions, so the tangent line here generates the y value here. Oops, sorry. The y value here, this is the derivative here in purple. And then when you think about collecting all of those y values, I could put a tangent line at this new point. And then now the slope of that tangent line ends up generating a new derivative, its derivative, the derivative of the purple. And if I look at this point, and as I drag all of this about, then, oops, we can see this pattern of what that next derivative is. So the main takeaway here is that as we're generating these, you should be able to sit here and go, okay, that third derivative or fourth derivative or whatever is just the derivative of some other function. It's a tangent line put on some other function. So I'm going to erase some of these marks here and then ask some questions. So let's go ahead and show that second derivative here. And I'm going to hide my tangent lines. So let's think about the green here is the original function. So let's think about position. Okay, so green is a position function. We have its derivative, its rate of change would be purple. And its rate of change would be red. So if I was trying to model this, so the x-axis here is time. So something maybe I haven't said yet, when we're looking at these derivatives, notice that since you keep drawing them at that x value, that the x here is always time. The y, though, value will change. So if it's the position function, it's a distance. If it's a velocity function, it's a rate. If it's acceleration, then it's the rate per some amount of time. So let me put a point somewhere, like here. Okay, so there's a point on the original function. It's 0.35, 0.53. We have a point on the purple function, and it doesn't look like I gave the point here in the acceleration, but I'll do that. Oops. And so what we want to do is be able to describe a behavior. So if this is velocity, position, and time, can I say what is happening at this moment, this random moment that I stopped at? Just trying to get it so we can read all of those. So which way is it moving? Is the object moving right? Is it moving left? Is it speeding up? Is it slowing down? Take a second, try to decide, see if somebody next to you is at the same spot, agree or disagree. So is it moving left? Is it moving right? Is it speeding up? Is it slowing down? Okay, so the question of right or left. Right or left is answered by the derivative. So notice that the time is 0.35 seconds. That's really what all of these are agreeing with. So at 0.35 seconds, we are at a position of 0.53. So if I was thinking about I'm moving left and right, so if I'm just moving back and forth, and if I started somewhere at like 0, if I call like thinking about the coordinate system, this is 0. So it's just saying that I have made it somewhere over here. Well, how did I get there, or what am I doing now, is not really told by the position function. So the velocity, though, if we think about slope, the rate of change there, that the velocity is 2.77. Okay, so that means I should have said moving right because my velocity is positive. Now, am I moving to the right? Am I going to be moving to the right faster or slower? And you should have said faster. The acceleration here is positive. Again, sometimes people are misled that the acceleration graph is decreasing, but it's still positive. So it's still accelerating. It may not be accelerating as much as it was a moment ago, but it's still accelerating because it's positive. So notice that it's this moment right here where the acceleration becomes negative, which means that if I would move this along, So it's in here, I just crossed it, where we would get a change to happen. Do you notice that the moment the acceleration graph crosses is the moment that the velocity graph starts to bend back toward the x-axis? Which should make sense. Positive velocity. Think I'm going up. The ball is going up, rocket's going up, but the acceleration is negative. You would have it slowing down. And so the velocity here is approaching zero. But do you notice the position graph is still going up? Why is the position graph still going up to here? Think about it. Because the velocity is positive. Okay. It's not as positive as it was a minute ago, which means the graph is flattening out, but it is still approaching some max. So the key here is to, can we interact with these graphs in a way to describe the behavior? So notice that if I move over here a little bit further, that this is a moment where the velocity is negative, acceleration is negative, and so we're moving left. And this meaning would be that we just got back to zero where we were thinking maybe about starting. Okay, so let's do here something different. If you Google, excuse me, if you Google moving man, and you see this website from Colorado University of Colorado Boulder, you have this little ability to run this fun little simulation. Notice the Java that I chose there. So when this loads, we're going to be able to manipulate and see the graphs of velocity, position, and acceleration together. So first, I can record one and then try to interpret it. We can, sorry. We can manipulate some of the graphs here and things, and so I'm going to actually click this that says charts first. Maybe I'll just go here. So first, we have this little guy, we can move around. It's trying to track the velocity. I can make him stop. I can type numbers for velocity, and just notice how he's moving. Consistent, right? 1 meter per second here, always 1 meter per second. But I could go in here and now also type some kind of acceleration, like minus 0.5, and opposite, slow down, negative, change direction, speeding up in the negative direction, they are green. And then there's actually these walls that he'll run into and cause the simulation to stop, or you can just um, remove them if you wanted to see him keep going. Okay. So what we're going to do is I'm going to stop that. And we're going to go here to the charts. Now, if we try to drag the guy about, you'll notice how jumpy these values for the velocity and acceleration end up being. It's like registering too much of just my finger moving on the touchpad, and it's just not smooth enough. So I'm going to try to do this by typing in just values, and we'll see how the graphs would change. So I'm going to get rid of the walls, and I'm going to set a starting position here at minus 10. So that means we're just starting left 10. Okay. So if I start with a positive velocity of, let's say, 2, and go ahead and play that, velocity is constant. 2 a bit. Notice that the position is a line, right? So when we think about slope, the slope here is always 2. The line y equals 2x with an initial value of -10. And there is our simple relationship. Notice here the acceleration is 0, right? There is no change in velocity, 0. All right, so I'm gonna reset, and I'm gonna put them back here at -10. So if I want an acceleration to, let's say the acceleration is constant, it's a 1, and I'm gonna start out not moving. So velocity is 0. So the graph should start here for velocity. But if this line, so I'm going to have to zoom this. So if the acceleration is always the number 1, y equals 1, right? Think about what this graph would look like. And then think about what this graph would look like. You should be able to try to sketch that right now. So pause it if you didn't do that. But here should be what you're thinking. Horizontal line of slope 1, quadratic. Notice that as his velocity is increasing, obviously his position is changing faster for the same amount of time, right? Because he's moving faster. And so there is the link between those. So what we could definitely do, and I'm going to do, is that I'm going to choose some things here. So I'm gonna pause the video. I'm going to set some of these parameters and then record that. And then you are going to try to decide in words how the little guy was walking. Which way was he walking? When was he walking? Left, right, speeding up, slowing down, all those things that we've been talking about. So let's do that. Okay, so here we have Here we have the position, velocity, and acceleration. So where did he start? Right of 0, left of 0? Which way does he walk? Does he walk both directions? Does he only walk left, right? And how is he walking? When is he walking faster? When is he walking slower? So try to answer those questions looking at the graph. Pause the video before you look at the solution. So I hope you have your solution now. So let's watch the playback. Okay, it wouldn't let me play back. Try again. Oh, that's fun. So we lost the first bit of the video there for some reason. So, so what you should have said is he started to the right because positive y value. That notice that he never gets back to 0, at least in this part of the walk here. His position is still above, and then he starts walking. So he's walking toward. So he'd start walking toward and then away. Um, and velocity. So walking left, change direction, walking right, acceleration constant. Let's do another one. So notice here that something's really different about this one, but which way would he start walking? Um, so he's actually standing at his initial position, which you can see is -5. So should he start walking to the right, or will he be walking to the left? I'm going to zoom in on the acceleration graph here. You can see that maybe a little bit better. Zoom in just a bit on the um, velocity here as well. So, walking faster, walking slower, you should definitely be able to see all of those pieces there, or even walking at then a constant rate. So here we go. Notice he's about to change direction. The velocity is almost negative. Velocity's 0 and velocity is negative. Notice that the acceleration was negative that whole time. So it's the slowing down again that we see, velocity, that velocity in here, like that um, as this curve is coming down, he was still moving to the right, but he was moving slower to the right. So just an observation here, when we think about these functions, you notice that it didn't exactly make discontinuities here. Because if this was vertical, then that would say that the acceleration was infinite, and then you would explode and no longer be in existence. So we really would have to be moving in a way, like even thinking about corners, right? Like thinking about how that would look here, that that would mean that there's something then that would be an discontinuity in the next derivative, which actually has the name of jerk. And so that also shouldn't be the case, but that's just the limitation here of it. So here's where this then takes us. What if I only showed you one graph, right? If I only showed you this graph and I told you its velocity, could you then tell me what this person is doing, how they should be walking, just based upon this information? And so I would hope that you could look at this and go, oh, positive velocity, constant velocity, still positive velocity. So here, so we know looking at this graph, walking right all the way till just after 6, and then there's some idea of walking left. Notice we don't know how far, okay? I don't know how far they've really walked right or left. Like I lose that information in this graph. The position will tell me how far, right? It's going to tell me location of where I'm at, and if I know where I started, I could figure out how far I walked. But that information is lost here. Second semester, we'll figure out how to get it back. And acceleration, like acceleration, should be easy off of this graph because if this is the derivative, it's the slopes. So whatever that slope is should be whatever this is. So if this was a quadratic, then this would be some other kind of linear function. So what I have here for our last piece here of 3.4 is to look at the graph of a derivative. So if this is a velocity graph, and if I tell you f of 0 is 5, answer these 4 questions about that behavior. When is it moving right? When is it moving, when is that at its maximum position? When is the acceleration positive? When is the velocity positive and the acceleration negative? Um, this one I'll tell you, like when is the position at a maximum? is a little tougher to decide, but see if you could think through a reason why you would know that. Okay, so pause the video, think through this, sketch this graph, put these 4 comments here, and you should be answering intervals of x, or really t here. So, and by the way, these should be open intervals. So like at this value of 2 seconds, notice that 2 seconds is included in 2 different parts. Like there's a change happening at 2 seconds. So we're not going to include 2 in either portion. Okay. So think about this answer. Take 30 seconds or so, write out your intervals before you go on. Okay, so when is the particle moving right? Well, if this is the velocity function, which it is because it's the derivative, we should be moving to the right when time is greater than 0. So that should be this part of the graph. So the answer to 1, 0, okay. So on that interval, velocity is positive, particle is moving to the right. When is the acceleration positive? I'm going to skip number 2 for just a second. When is the acceleration positive? Well, if this is the derivative, the acceleration is I hope you said derivative or thought derivative, which is the slope of the tangent line. It is not the tangent line itself. So positive slope, 0 slope, negative slope, positive slope. So the acceleration is positive whenever I was saying positive slope. So for number 3, the solution should have been the interval from 0 to 2, and open intervals, and then also from 6 to 7. So it's really the union of those 2 sets. So any time corresponding to that, the acceleration is positive. Now, that doesn't necessarily mean that it's moving right or left, right? Because think about something going up or down. The acceleration could be negative the entire time, and it moves in both directions, so don't overlap those. So acceleration negative, velocity positive. So acceleration negative is this portion and this portion. Velocity positive. Now, careful, don't look at slope. Like the moment I start looking at slope, that's what I just answered here for negative. So if the velocity is positive, this graph is velocity, it's looking at y values. So it looks like the green portion is what we want. I have a negative slope at every moment, and I also have a positive y value at all of those moments. So we should have said 3 to 5. Okay, now let's deal with the position question. What is the position of maximum? So when I think about how this is starting, I wonder if I could think about, like, if this was something moving left or right, like the little guy walking. So when time is 0, it's starting at 5. Okay, so this is t equals 0. Now, he's going to start walking, so positive velocity, positive velocity, positive velocity. He's walking to the right for 5 seconds. Right? He's here now. Okay. He then is going to walk left for 2 seconds. So he's going to walk back. Now think about what that means. Now, I didn't ask what is the position? How far does he end up to the right? Like, I don't really know that distance. But I do know when he is furthest to the right. So he's definitely furthest to the right 5 seconds later. So when wrong one, t equals 5. Which means if I could come up with a position graph, I should be in 5 seconds, some idea of a max. Okay, furthest right, he changes direction, starts walking left. Okay, so I hope that gives a good start here to point 4. If you do need extra help, there are 2 additional videos that will be really different than this one from a previous year. You can click on that link on the left of the videos of all the lessons. You definitely have some MyMathLab multiple days of this, and we'll continue to work on it.